Okay, as Alan said, I'm Mark Reid from Johns Hopkins Applied Physics Lab. I'm briefly going to talk about some work we did on the Van Allen probes. Just go ahead and give up the agenda here. We'll go through a brief introduction of the Van Allen probes. Many of you may have heard of it referred to previously as RBSP, or the Radiation Belt Storm Probes. We renamed the mission after launch in honor of James Van Allen. So we'll go through a brief introduction. We'll have a rationale of adding onboard data compression. It was not in our original baseline. We didn't launch with it, but we added it post-launch. We'll look at the recorder management software, give you an overview of that, talk about the requirements we added, give you a high-level design, and how we're able to configure it. And I'll talk through some of the considerations we had when putting compression algorithms into flight that we had to make sure we took into account. And then lastly, we'll look at our performance and give you a little bit of conclusions. So an introduction, the Van Allen probes, it's a NASA mission out of NASA Goddard to study the near-Earth space radiation. We consist of two spacecraft. They're identical in every way except for the separation system because of the way they were stacked at launch. So they're pretty much identical spacecraft. They each host 5 instrument suites, and that's a total of 10 instruments per spacecraft. So we got 20 instruments spread across the two. And at launch, we had a build that had 17 applications and 8 libraries. We're built on top of NASA Goddard's Core Flight Executive. So anyone that's familiar with that, that code is packaged into applications and libraries. So we implemented 17 unique applications. And as a presentation, you'll see some of those. I don't give you the full picture, but you'll see some of the applications. So this presentation specifically looks at an 18th application that we loaded post-launch. So basically, we just added a new application. So our rationale for adding compression. Post-launch, we actually started looking at the data we were getting returned from the spacecraft. And there was some indication even prior to launch, a lot of the science teams would have liked to have had more data. And I think that's sort of always the case. Science teams want more data. The more data they have, the more discoveries they can make. So in looking at how we could get them more data, we took 2 weeks of observatory data, and we just used basic gzip compression. And we played with turning the dials up and down a little bit on gzip to determine what kind of results we could get. And we got a decent reduction of some of their data. So if we could get approximately a third compression out of there, that's 50% more data. We turn 100 into 150. And then the next step is, once we had just played with the data on the ground, because now we're getting real data from the spacecraft, as opposed to pre-launch, we could look at some canned data, but it wasn't representative of what we're really going to see, because we didn't know what the entropy of the data was going to look like going through the radiation belts. How dynamic was the data. But once we were able to get sort of a real feel for how the data compressed, we created a prototype application, and we loaded it up on our flight software test bed. And our flight software test bed, it is basically a form, fit, and function RAD 750 with our spacecraft interface card, solid-state recorder. So we're running on the flight hardware, basically. So we knew what kind of CPU utilization we were going to get once we put this prototype app into our test bed. And we estimated that it could require, about 5% of our CPU, which is not too painful either. And it did have a pretty small memory footprint. And we looked at what type of effort it would take to actually take that prototype, turn it into something real that we could fly. And it turned out, with a little cleverness in the design that you'll see, it really ended up only being about 3.5 staff months of effort that wasn't in our original baseline for post-launch maintenance, and about 4 calendar months to implement it. So we launched August of last year, did this evaluation through sort of the November, December timeframe post-commissioning, and then we were able to get this code up around April of this year. And it was deemed low risk and pretty transparent to operations, again, based on how we decided to implement it. This may look like an eye chart. I'm not sure from the audience view. This is sort of an overview of our solid-state recorder and how we manage it. On the upper right, what you see is effectively it's a file system. It really is a DOS file system. So that is the directory structure of our solid-state recorder. There is a record directory, which we call REC. and that's where files are recorded. So files are just put in this record directory, and when they're closed, they get moved to a priority directory for downlink. And that priority directory is determined at the time the file's open. So when we open a file for recording, the highest priority data would go into the lowest number. This is like VxWorks. The higher the priority, the lower the number. So the P0 directory is our highest priority data, P1 next, P2, P3. So P3 is the low priority data we might get to, we might not, when it comes time to play it back. And then the trash directory is where we hold data. Once it's been played back, we have the option of just go ahead and delete it or just put it into trash and then let mission ops determine to delete it or not. So the operators have control over that. That's the directory structure. What's on the left is really the flow of how data gets recorded. The two upper left bubbles, IM and SI, those are applications. So those would be CFE applications. The IM is an instrument manager, and that interfaces to all the instruments, pulls in all the data off the payloads, and throws it onto the software bus. So it takes the packetized data, throws it out to be routed, to be recorded. SI is all the spacecraft interfaces. And then all of our other apps can also generate housekeeping, which would be thrown out on the software bus to be recorded. Then the REC app, which is sort of upper middle, that's the record application, which is going to basically subscribe to all that data and record it into files in that SSR rec directory. So it just opens a file in the record directory, writes data to it. And once it's done, it would close that file, move it down to a P0, P1, P2, whichever priority directory, to be picked up by playback. So then the playback application is the next app in the pipeline. It would say, oh, there's a new file to be played back in my priority directory. I'm over the ground station. I've got downlink. I'm going to play this file back. So it opens that file, moves it to the downlink directory to play it back, and then eventually would either put it in the trash or delete it. We tend to run class 2 CFDP, and that's it's an acknowledged mode. CFDP is the CCSDS file delivery protocol. It has the handshaking, so when we send data, the ground can handshake back and say we got it. In class 2, that's the acknowledged mode. So in class 2, we would just delete the file. There's no reason to hold on to it. We know the ground got it. So it's really only in class 1 that decision to move it to trash makes a difference. So anyways, this playback is playing the data back. It's building up those protocol data units for CFDP, and then that goes to our telemetry output, which writes it to the hardware. So TO is like an interface task to the downlink hardware. So out of our 17 apps, you've seen 5. So again, we looked at what it would take to add compression, and then we said, well, what should we add, and what would the requirements be? And when you see the next chart, you may see how we derive the requirements. But what we add, we actually keep our requirements indoors, and we have criticality assigned to them, and a software build number and an application name. So we're going to create a new app called it Zip, and that's what we allocated these requirements to. So we put up requirements to basically do compression at the packet level, not at the file level. And there's a reason for that, and we'll talk to it a little bit on the next chart. And to be able to enable and disable that ability to auto-delete, we want to have that same ability on compression. So we could compress the file, we could keep the uncompressed file, or we could delete it once we had the newly compressed file. It's useful for testing, not so useful on orbit. And we also wanted to be able to report our, that state in telemetry and have some counters and error events and that kind of thing. So how did this change our software? So again, we kept all the existing applications that you saw on the previous chart intact, and we just added a new zip application into the pipeline. And what you'll see is the zip application is just going to pick the files up from the record directory, compress them, and put them back in the record directory. So he's just one more step in the pipeline. So there was a small modification we had to make to record, because what record was doing when it finished recording was move it to a priority directory for downlink. We had to say, no, don't move it out of that directory. Leave it in the record directory. So there was a small change there. And then the zip application would just operate on that recorded file. And then it would place it into the priority directory for downlink. And then the rest of the pipeline's the same. The other applications that we had small impacts to, you think, we can just plug this application in. But there are other applications in the system that might need to know about the data that the zip application produced. So, for instance, the zip application, from its requirements, had to produce some counters and some events and those kind of things. So when it's going to produce these counters, it has a housekeeping packet that has those counters in it. Well, how do those get recorded? So we had to make another small change to our telemetry output, record, autonomy, a few other applications that required that data. So this is an exercise, if you want to think in hindsight, of how easy it is when you plug in a new application to make sure you connected all the ripples of anybody else that needs to subscribe to that data. Because this is a publish and subscribe architecture. I can just plug this thing in with its blinders on, and it can take data and produce new data. But now, record, autonomy, these other apps might want to look at that new data that we're producing. We have the autonomy application. I think you'll get a briefing tomorrow which talks a little bit about the way we do autonomy at APL, and may also talk a little bit to what was done on Van Allen probes. But it's basically an application that subscribes to all the data and then makes decisions, like a rule-based decision engine that'll make decisions to either safe the spacecraft or take some other action based on the data that's being produced. Okay. So at a high level, what did we do? We have sort of an application framework which has a main package which has all the main functions of your app. And that interfaces with CFE. And then we have sort of an application specific and the commands for that app. So we decided to create this new zip app. So we've got those three packages sort of out of the box. And then what algorithm did we use? We went to basically the zlib, basically gzip, and we took it at the lowest layer down at the deflate layer. There's a few different layers in that library. There's deflate, which works sort of on buffers or pointers. You can think of it like I've got a buffer of data, and I can pass the pointer to that buffer to a deflate call, and it'll stick the output in the new buffer. Versus, I think the gzip type calls are working sort of at the file level. And in between, I think there's a layer called compress. So you got like deflate, compress, or gzip. So we took it at the lowest layer to kind of work on the buffers because we want to be able to zip packets. And we'll talk about why in a little bit. But then that deflate package only used two other packages in the zip library, which were these trees, and the Adler32 package, which is sort of like a CRC algorithm. And so, I might have to go back just a little bit. This is sort of we decided we'd want to be able to configure what we can compress and what we didn't want to compress. And you may remember that we had the concept of priority directories of P0 to P3 that determined what order things got downlinked in. And what we wanted to do is just have a table that says, because we actually have three file systems on board. We have an EEPROM file system that has our code in it. We have a RAM file system that we record events and those type of things in that survives a reboot, oddly enough, and lets us carry data. If we were to lose our SSR and not be able to mount the SSR, we would have information in the RAM file system that told us what went wrong. And then we have our SSR, our solid state recorders file system. So basically in the left column, we just say, what device am I looking at? So for the SSR, for the input path of the record directory and an output path of the priority 1 directory, take any file that has a 1A rec in the file name. And the 1A is a priority instance pair that says what the priority of the data is. The instance indicates which instrument suite it's coming from or which type of data it is. And then we're just going to zip it and replace the file name string with the new output. And so it says deflate as the action. Or you could just say rename it. Don't even bother to deflate this file. And examples of why you might do that, the 1B file for us contains spacecraft event data. And they actually want to dump that. When they get the spacecraft in contact over the station, they just want to dump that and get it immediately. And they don't want to have to wait to deflate it, or inflate it, I guess, if it's been deflated. So we don't even bother to zip it. So here are some considerations that we had to take into account. One is, as I said, we try to use Class 2 CFDP. At least anytime we're over at the APL station, we use Class 2 CFDP. If we're not over APL station, And we do use a couple of different stations. We use a station in Hawaii and a station in Australia, I think. If we're over either one of those stations, we dump the data, but we don't get any acknowledgement back that they got it. There's no closed loop on those stations. And if there was an interruption in the downlink and you lose a piece of data, in our case, if you had zipped at the file level and you lose a piece of a compressed file, how do you uncompress what's beyond that? So the consideration we made and the trade we made was we would zip on like 4K chunks. And we would accumulate CCSDS packets into a 4K chunk, compress it, put a new packet header on it, and send it. So what you'll see is we have a bunch of non-zipped packets that we put into the data portion of a new packet with a new 12-byte CCSDS header that has the app ID, sequence count, length, and timestamp. And we zip it, timestamp it, and gets re-recorded. So the output file is a mix of zipped packets and non-zipped packets, because we may make a decision that once we've zipped it, it's actually bigger than it would have been if you hadn't zipped it. And that is possible, that the deflation actually increases the packet size with the algorithm and based on the data you're given. And so the ground software, or the unzipper, basically keys on that app ID to say, oh, this is a zipped packet, takes the data portion, feeds it through the unzipper, and then pulls the packets back out. So we're not zipping files, we're zipping packets and then re-recording them back into files. So as I said, the zlib deflate package that we chose to use, it works on the block or buffer level. So we have an input buffer and an output buffer. We accumulate up to reading out of a file up to 4K bytes of packet data, zip that, put a new header on it, send it, re-record it, I guess, back into the new file. So then if you were to get a corruption on an unacknowledged mode downlink and we missed a frame of data, the only thing that you're missing is the piece that was in that frame. Everything else is uncompressible, right? Because each thing is compressed in its own block. And then we had to choose, we made some decisions, and these were talked about a little bit this morning. No dynamic memory allocation. So we basically removed all the dynamic memory allocation and used only statically allocated buffers. So if you took the library off the shelf, you need to hand it like a pointer to a new function, pointer to delete. So when you say compress this, it would new and delete things. We don't do that. So we replaced those with statically allocated buffers. And then we had to choose compression levels. And we played with the dials sort of based on our data. We didn't want to give the operators the ability to freely command this, but we settled on compression level 6, which is pretty good compression versus the CPU usage we had. We also played with the max memory level, max window bits. So anybody that's used this library may know these parameters, but that basically sized our footprint. So what we ended up with was an application that took 14 kilobytes of EEPROM, the application itself being compressed, and then 100 kilobytes of RAM approximately, and takes about 5% of our CPU. So let's look at a few plots I have. I just have a bunch of plots now, and these should go quickly, where we look at the performance. So our recorder, we have a, trying to think, 2 gigabyte recorder. I'm trying to remember the recorder size. But it's sized to basically support 2.5 days. So what you would normally see on a daily cadence is we get to about 40% full of each allocation. So each instrument has an allocation on the recorder. And they should use about 40% of their allocation, and then we play it back. And you'll see there are a couple of cases there where we got to play back. The vertical grid on this plot is 12 hours. So 2 grid lines across would be a day. So there's a good peak that's about a day, and we played it back about a day, and we played it back. And then when we enable compression, you'll see that the peaks, and especially the blue peak, which was the ECT suite, came significantly down. So by compressing their data, now we're only using about 25% of their allocation on that cadence. And the bottom plot is showing CPU usage. So you can see when we enable compression, the CPU gets a lot noisier and chattier. And this is a CPU chart. Our downlink, we run at a 2 megabit per second downlink rate. For most of our contacts, we can go as low as well, kilobits for emergency mode, but typically like 500K, 1 meg, 2 meg are the type rates we run at. And there's some spikes where we do, there's allocation management that works on the recorder to make sure no instrument is over its allocation, and that runs as a background task. But you can see when we enabled compression, it's also running as a background task I put in the blue box. The CPU will spike up whenever that runs. Again, it's a background task, so it doesn't really matter. But if you look at the average CPU load, which is the blue line, again, it's noisier, but it's not really a significant difference. And sort of the average, if we were to average that average and smooth it out even more, I guess, it turns out to about 5% or so. It's kind of almost lost in the noise. And we do tend to run between 2 modes on that playback, like 30 to 50%. Like 30 is sort of like the downlinks kind of idling, and then the 50s we're really hitting it more heavily, I guess. So some more examples. So by data type, obviously spacecraft housekeeping compresses really well. If you think about housekeeping data, it's really a bunch of counters and voltages, temperatures, things that aren't changing a lot. This was the one science instrument suite that compressed the best, the ECT suite. And you'll see there's a noticeable dip down with the horizontal axis here. These are file names where the beginning of the name is the mission elapsed time. So that will translate to a real time, like a year-day time, but the conversion isn't here. This is about 1 to 2 weeks worth of data, I believe, on these plots. But there's a noticeable dip down over about 2/3 of the way across the plot. That's where the instrument actually had turned off their high voltage for a short period of time. And so their data was a lot more static, I guess. It wasn't changing as much, and therefore became more compressible. And here's like another example for EFW, one of the other instruments. And the hump on the far right was a solar flare where their data became a lot more noisy and didn't compress as well. Other instrument data. This one was interesting because our magnetometer data is already compressed by the emphasis instrument through their DPU. They send us compressed magnetometer packets, but we're able to concatenate those packets together into a 4K chunk, and then it compresses even more. And it surprisingly compressed very well. So conclusions. What led us, we were actually able to review some on-orbit data, which led us to consider the benefits of this. We'd actually considered it pre-launch. We considered it way back in Phase B, I think, when we were trading instruments and DPUs and interfaces. At one point, they were doing compression in the instruments. At another point, they weren't. But basically, our baseline design, through build and INT and launch, did not have this capability. But looking at the data on orbit, you're actually able to get a real feel for what the data is going to do, which you may not be able to get as easily, looking at an instrument on a bench. And then we looked at readily available compression software, and it does easily transfer into, if you have a nice architecture that you can plug it into, it transferred very well into our architecture. And then just really a small effort has really given them quite a bit more data. So we're looking at reusing this application with the CFE framework. You can use, pick this application up and use it on our next mission. So it should provide us benefits on future missions. And I think that was all I have. So are there any questions? I don't know if I went too fast or too slow. I think I went fast. Getting us back on track for a break.
That's what software does, sir.
I'm guessing that your compression algorithm is lossless, right?
It is lossless compression.
Okay. And also, since your CPU utilization went up from 70% to 90%, were there any side effects came from that?
Yeah, actually, I can just real briefly. I'll go back to that chart. I think you're looking sort of in this area.
Yeah, 90% is kind of a green flag.
Yeah, you can think of this like it's a background task, like our memory scrub or any other background task. So you'll see there are already some spikes sort of on the left-hand side, where there are some spikes up near the top of that. I guess you can see the light gray spikes up there, where, say, maybe our memory scrub task or maybe our allocation manager one of the lower priority background tasks was running. It's just when compression is running, you just see a lot more chatter up in that area. But the actual sort of average CPU loading, any high priority task with a tight deadline is going to get a run.
So there were no bad side effects?
No, there really aren't any side effects to it.
Okay, thank you.
It's a good question.
Props on zlib. It's sweet, even though it's KNR.
Right.
I'm just wondering why you chose to compress the 4K, CCSDS packets rather than the file itself and then chunk it, because then you're wasting additional overhead over the course, and through your file transfer protocol or this FDS that you or FTP.
CFTP.
Yeah. We all do proprietary, so we don't know from CCSDS. But you're going to get the entire file down, or you're going to retransmit the chunks of it that you've lost. Right. So why go with the extra overhead?
I think that the one piece you may have missed is, because I did speak really quickly, there are two different modes for CFTP. There's a Class 2, which is an acknowledged mode,
right,
and there is a Class 1, which is an unacknowledged mode.
Right, but then you move it to the trash directory, and it's up to the ground too.
That's actually one of the decisions the ground had made, was that they, even on the unacknowledged mode contacts, they wanted to make sure that if we lost data, that you could still uncompress that data. So that's why it's sort of a constraint. You can think of it as a constraint we put on ourselves to block it into nice sized chunks, that if we miss a frame of data, we miss a 4K chunk. So we miss some integral number of packets. We don't miss a whole 10 megabyte file.
That's part of the trust. Yeah.
Right. So
Thanks.
yeah, it's really just it was really just to support the Class 1 CFTP.
So something that was sort of implicit in sort of just that you sort of, in a sense, sort of glossed over was sort of the simplicity of just plugging in this compression function, and just you sort of did it in stride, and it didn't seem to be an issue. And I don't know how many projects would be able to make such a change to their flight software. So your design, your overall flight software design must have been very simple or elegant, that it allowed you to do that.
The piece of our architecture that allowed us to do that is actually NASA Goddard's Core Flight Executive. The CFE publish subscribe architecture, being able to plug and play applications, allows you to be able to, each application really sort of works in its own world. It doesn't even know the other apps are there, other than the data it subscribes to and the data it sends onto the software bus. So in this case, just being able to pull data from the recorder and re-record it sort of with blinders on.
Okay. And sort of that leads to my sort of second question, is sort of what I've seen with APL spacecraft is sort of the adoption of things like CFE, CFDP, and lots of other either coding, standards or frameworks or what have you. And it seems to have worked well for lots of your missions, because every mission I see from APL is either using CFDP or something, and it seems to work very well for what you guys do. So I don't know if you have any comment. There seems to be a commonality across all your missions. In some other organizations, you may not have that sort of commonality amongst flight
I think there's
software.
some benefit there to the size of our software group. Maybe I'm not sure how we relate relative to JPL's software teams. And also more recently, I think some of the partnering we're doing with NASA Goddard has helped us a lot in being able to leverage things from others.
Any other questions? One? No? One here? I guess not. Nope, I guess not. Okay, thank you.